Okay, so let me just go through this very quickly. A norm on V, and maybe you can just sort of speak along as I go. A norm on V is a map from where to where?
V
V
to
to R positive.
Yeah, exactly. Sorry. Only a certain amount of hurry is workable. Otherwise, you just start making mistakes. Okay, so this is from V and it produces a non-negative real number such that, oops. So what are the properties? Three properties. Oops. Okay. So what is the idea of a norm? A norm is a way of defining size. So only the zero vector has zero norm. The norm is homogeneous. So norm of lambda times x is lambda times the norm of x. This is morally speaking correct, but really I'm measuring sizes of numbers also, right? So for all x in the vector space and for all lambda in the field. Remember, the field is real or complex numbers, and that is just the usual absolute value, which is a non-negative real number, and the all-important triangle inequality. Okay, so examples. Rn under the P norms. And we, in fact, last time saw the examples 1, 2, and infinity. And mostly we will stick with usual Euclidean distance. And for the purposes at hand, it will not really matter which distance we will use for the most part. Okay, that statement I will make precise. Okay, so so mostly we will just to use our ordinary Euclidean distance to visualize things. Do we need to prove any of this?
I guess, strictly speaking, sir, we would need to prove that these P norms do satisfy the axioms, but I think we did these last class.
Well, we certainly did do it for, okay, so let's just, okay, so proof. So P equal to 1. So x1 is equal to sigma xi, for x is just our usual row vector, sigma absolute value of xi over I. So is it clear that this satisfies properties 1, 2, and 3? Okay, so I'm going to take that as a yes. So P equal to infinity, this was the thing. So what was the definition?
The maximum of x1.
So maximum of all the individual absolute values. All right, so is it clear that this satisfies the triangle inequality?
Yes.
All right, so you have to do this carefully. But I will, okay, so how about P equal to 2? So here it's the usual Euclidean distance. And from now on, if I do not really mention what distance we are using, then it will be the Euclidean distance. All right, so what's the definition? This is the square root of, so sigma xi square. And then I take the square root of that. Okay, so question. So properties 1 and 2 are quite easy to see. Can we all prove number 3?
So proof for what?
All right. So property number 3, the triangle inequality for the usual Euclidean distance. Of course, you can just see it in the plane, right? And even in 3 space, but can we prove it in general? Do we want to prove this now?
Or p greater than 1, the triangle inequality.
Yeah, so this is, the triangle inequality for our usual Euclidean distance. So does everybody know how to prove this?
We can square both sides, then it's obvious.
Okay, so maybe just a few things. All right, so let me just, so proof of this, proof when field is R. So let me just, so you can do several things. There is a slick proof using a discriminant by writing a suitable quadratic equation. So this is equivalent to showing what? Both sides are positive numbers, right? So sorry, not this. What am I doing here? Proof of property 3. So what do we have to show? We basically have to show the following. Sigma xi plus yi the whole square. All summations are over I unless I. So why do I not write absolute values anymore? Because xi and y are real numbers. So when I square, everything is going to be all right. So what do I have to show? Come on, this should be.
We need to show that this is less than or equal to summation of xi squared plus summation of yi squared, that whole thing squared.
Well, not quite, no?
Not quite right, yeah. Root of summation xi squared plus root of summation yi squared, the whole thing squared.
Correct. So basically I have squared both sides. And so how do you go about doing this?
So first, like you expand the bracket on the right hand side, then you'll get, and then you expand the square summation on the left hand side, like summation of square, right? So expand the square inside the summation, stuff gets cancelled out.
So you more or less follow your rules, correct? So, and do algebra. Finally, what does it boil down to?
Cauchy-Schwarz inequality.
Right. And what is the Cauchy-Schwarz inequality? The reason why I'm saying this is because I'm doing this for real numbers, but then I want you to do everything over complex numbers also. So some conjugation, etc., is going to be required. So what is the Cauchy-Schwarz inequality?
Sir, x1, y1 plus x2, y2, etc. Is less than or equal to square root of x1 square plus x2 square into square root of y1 square plus y2 square.
Correct, exactly. So, etc. So do algebra. See, it is enough to prove the following. And let's write it in this way. What is that?
Standard inner product.
Okay, so again, this works because xi and yi are all the x's are real numbers. If they are not all real numbers, then what do you do?
You define the inner product like with the conjugate over yi.
Correct. So was this done in your linear algebra course? Hermitian inner product?
It is there in the notes, but I don't know if I don't actually remember if sir had time to cover it in much detail.
All right. So this is an important thing. So I'm doing this for real numbers, but I'm going to ask you to do this over complex numbers. All right. So this is an interesting thing. So what kind of gadget is this? So notice. So do algebra to see. So this is the thing that we really need to prove, and that's your Cauchy-Schwarz. Okay.
So shouldn't there be a square in the left-hand side?
I'm sorry. What are we saying?
In the inequality which you wrote, Cauchy-Schwarz, shouldn't there be a square on the left-hand
Right.
side?
Yeah, sorry. Okay, because this is just not, yeah, exactly. Sorry, the square. All right. And so when you expand everything out, this really just comes out to be, and take everything on one side, you can write everything as a sum of squares. So check this. But etc. Where and so just note here that norm x the whole square is just xx, correct? And other things, how do those two things compare? It's symmetric, and this gadget is linear, is R linear, sorry. In each argument, in each slot. Is the meaning of this clear?
Sir, could you just explain what R linear means?
Okay, so okay.
R
So,
linear as in like every term is linear? Is that what you're saying?
okay, so let me just state this. i.e. x1 plus x2 y, and let's just say rx1 plus x2 y is equal to r times x1 y plus x2 y. Oh, this is bad. This is bad. Sorry. This is because subscripts cannot both simultaneously be components as well as vectors. I apologize. Notational. So suppose x and x prime are vectors, and I take the linear combination of vectors rx plus x prime in the first slot, then I can break up the addition as well as pull out the scalar multiplication. So for any scalar r, any x and x prime in whatever Rn. And similarly in second slot for whatever, if I put some linear combination over there. So is the meaning clear?
Yes.
Right. So that's what your usual scalar product satisfies these conditions. Is this true if I do the same thing over complex numbers?
Excuse me, sir.
Yes.
So what do you mean by the slot? Can you please tell me?
Oh, slot simply means that this is some kind of product, no? So this is the first slot.
Oh, okay, sir. Okay, sir.
And this is the second slot, right? It's a function of two variables, right? So whatever is the first argument is the first slot.
Is it equivalent
okay.
to saying it is bilinear? Is it equivalent to saying?
I'm sorry, again, come again, please.
Is it equivalent to say that this inner product is bilinear?
Equivalent to what?
Bilinear.
No. The bilinearity is not really equivalent to the formula. By no means. So I'm simply saying that these properties are true, that's all. And these properties you use in the
Okay.
it is really just a comment at this stage, nothing else. So if you want, what you can say is that the third property is saying that this function that you have defined on two variables on v cross v to r is bilinear. The second property is saying is that it is symmetric. And the first one, because of the formula, this is going to say that it's a positive definite symmetric bilinear form. The positive definite is something special over here. And in your linear algebra course, at some point you will study what the space of bilinear forms is like. And so what happens in the complex situation? How do I modify this?
The symmetry condition need to be modified. We need to put a conjugate on either side.
Right, because the definition changes in what way? In the box, the very first thing is the definition, right? The angle bracket of x and y. How does that formula change?
So we make it xi yi bar.
Or the other way around, depending on whether you want, you can have bar in the first slot or bar in the second slot. It doesn't really matter. But of course, you have to make one choice and stick with it. And then such a gadget is not symmetric, but
Skew symmetric.
But it is going, well, it is not. Skew symmetry is not really. Skew symmetry means that if you switch the arguments, then you get the minus. So this is called conjugate symmetry. The crucial property, though, is that, see, I want inequalities. And I want, so with complex numbers, there is no inequality. Can't say one complex number is bigger than another number. So the point is, so let's say this. Sorry, I'm just going a bit all over the place over here. Over C. Let's say, the point is, let's not use the norm notation here at all. Right. So that is the reason in order to make this definition, because I still have this idea that, just notice, no, because now in every slot, if both the vectors are the same, x and x, then I have xi bar times xi. So that gives you the norm of the norm square of the complex number xi, and I'm summing all of those. So this gadget is still going to be greater than or equal to 0, and it will be 0 precisely when the vector consisting of all the complex numbers xi, they're all 0. So this is a standard way in which you get positivity considerations for complex numbers. Okay. The point, though, is that you still have to prove this inequality, but that inequality is again just a matter of algebraic manipulations. Or you can do something more slick by considering x comma lambda y as so proof of expand everything. Or use that if I take then this has to be greater than 0. Unless x equal to lambda y. So how do you see this? Have you seen this proof? This is slick. So what you do is and now this as a quadratic in variable lambda. So this expression is going to be a quadratic in variable lambda. So how do I expand it? You see, I can just use bilinearity, right? When I expand this out, I'm going to get 4 terms. One of those terms will have lambda square. 2 of those terms will have lambda. And the third term, the x with itself, will not have lambda. But all of those are going to be just constants because x and y are fixed vectors. So if I regard this as a quadratic in variable lambda, then the number that I have obtained is always greater than 0. That means the resulting quadratic equation, if I set that equal to 0, what can I say? It will not have any solutions. This will never be equal to 0. Unless x and lambda y are, unless x and y are in the same line. So what is the upshot? How do I know that what do I get to say when a quadratic equation does not have any solutions, any real solutions?
Discriminant is less than 0.
Right. And when you write down that condition, discriminant less than 0, the Cauchy-Schwarz will just pop out. Okay, so this is a slick proof. All right. So exercise. Do the above proofs for yourself if you have not done it, and modify for the case where the field is. All right. So, okay. Any questions so far? Please do these things for yourself, okay? So, all right, so some more exercises. So let us say show so one is L infinity. This is the set of so this is the set of all bounded infinite sequences. So where all the xi's are, let's say, real numbers. So what is going to be the norm over here? Can I take the Euclidean norm? Can I just square all of these numbers and add them and take the square root?
So it may or may not converge.
Right, exactly. Just take, for example, the constant sequence 1, 1, 1, 1, 1, 1. Will not, right? So I have to have a different one.
Sir, we could try the lean soup.
Exactly. Well, we can just take the supremum, right? I mean, I have taken them to be, yeah, okay, fine. So I have taken them to be bounded, right? So this is just the, oh, sorry. What am I writing here? It's bounded, so I can do this. And in a similar vein,
No, is this pretty similar to the P equal infinity? No.
sorry, say that again, please.
Is it similar to the P infinity? No.
Exactly. So the only thing is that now I have taken infinite sequences, right?
Yes.
So correct. So that observation that you made. So this means that you can just take that proof and modify it. Just take supremum in appropriate way, right? And show that this works. And now here is another one, C01 is equal to continuous functions from the closed interval. Closed is crucial. Closed interval 0, 1s to R. And you see, in some ways, this is really the same example again and again. With what norm? So now I have to define the norm of a function.
So because it's on like compact set, you can just take the supremum.
Correct. So I do the same thing, supremum. But now supremum of what and over what set?
F over 0,1.
It's just f over 0,1. Yeah.
Right. So supremum, just evaluate the function and x in 0, 1. Will this work if I take open interval 0, 1?
No, sir.
Because the function need not be bounded anymore, right? So anyway, so it really is, our P equal to infinity case, it really is the same thing is being done again and again here, if you will. Of course, in the case of the closed interval, we are using a theorem over there, which you saw last time. Okay, all right. Just notice one thing, both of these spaces, okay, so these are vector spaces. Just take a moment to realize this. No, I can add such sequences, I can add such functions, and I can scale both of them. Both of these are infinite dimensional.
Sir, I had a question.
Yes.
Sir, the last proof that we did for Cauchy's first, so that just proves that L2 is a norm, right?
Yes, exactly. Yes.
I think I was thinking, I was hoping that we would do a proof that LP in general was
Right.
a norm.
Right. Okay. So, so somebody mentioned. So at some point we will do this maybe quickly.
Sure.
But for us, it is not going to be an important thing. Once we prove that. Okay, I was going to say once we prove that all of those norms give equivalent topology, but even otherwise, really, these three are good enough for us. So we do, strictly speaking, don't require that, but we will do the proof at some point. And anyway, as someone mentioned last time, right? So you can use convexity to prove this. So there are various inequalities, right? This Jensen's inequality or Holder's inequality. So you can use those to prove the arbitrary P case, P greater than or equal to 1, and see what happens when P is less than 1. We'll get to it at some point, but for us, it is not really an important thing. Okay, I do want to emphasize that. Mostly P equal to 2 case is good enough for us. All right. Okay, so continuing with definition. So last time we defined convergence of a sequence with respect to a norm. So let us recall that definition, and we will also now define continuity. So definitions. So when do we say that a sequence is convergent? Just quickly. Okay, I'll just write down a sequence. I think I called it SN last time. In a non-linear space V. Let's say converges to S means for all epsilon greater than 0, there is a large enough number there exists some natural number n. Oh, capital N, such that beyond this point in the sequence, you are in the, you have bounded the error by epsilon, such that for all n greater than n, and this was the point, Sn minus S is less than epsilon. And that norm was the norm in V, okay? And we say, okay. So for example, if I ask you to prove that a sequence, if it has a limit, it has a unique limit. How would you do that? Sort of one phrase answer using what?
Assume there are two and just take the difference between of those two and
And
half of that.
Right. And at some point use triangle inequality, right?
Yes, yes.
Okay, exactly. So, okay, good. Let's make now another definition, which is, suppose now I have a continuous function from one non-linear space to another, and more generally, let us say let S be a subset of a non-linear space V, and F is a map from S to W, another non-linear space. So VW non-linear spaces. Okay, so if you want, you can just pretend that V and W are both real numbers. Then what does it mean for this function to be continuous at a point? So F is continuous at some point in the domain. So let us say at V in S. What does this mean? Okay, so you must have meditated a lot on this definition last semester, I hope. For all epsilon greater than 0, there exists delta greater than 0, such that what happens?
If alpha minus the mod of alpha minus alpha is something minus V is less than gamma, then f of mod of f of V minus f of alpha is
so such that whenever x minus V, so the way to think of this is that epsilon is the challenge and delta is the answer, correct? So you say, well, you have to ensure for me that you stay within distance epsilon from the target. What is the target? The target is f of V. And you say, okay, I'm answering you that as soon as you take your x within distance epsilon from V, remember V is the point at which I am checking continuity. One has. So what does it ensure? As soon as I keep V within distance delta from as soon as I take x within distance V from delta. Let me see if I can get this right. As soon as I choose an x that is within distance delta from V, what does that ensure?
Fx minus Fp mod is less than epsilon. Norm is less than epsilon. Norm in W.
Right, exactly. Correct. So this is the exact same definition that we used last semester. The only thing that we have done now, following what we did for in the case of sequences, is replace the absolute value by norm. Correct. It's the exact same definition. Okay. So very good. So we have this definition. And I hope that nothing comes as a surprise now. Nothing in this definition is a surprise. So what we want to do now is, you see, we've been talking about norms. The norm is basically giving the size of a vector. But a lot of times, it is not really the size of a given vector that is so important as the norm of the difference between two vectors. So somehow we are thinking of this as the distance between 2 points in the space. So it's a related notion, but it is not the exact same notion. So let's sort of take a look at this idea that given a non-linear space, I can define the notion of a distance. Last time we already did this when we saw those balls, correct? But right now, so the idea is the following. So what am I doing? We defined a norm-linear space. We'll define the notion of a distance and see what properties it satisfies. Then we'll also define a metric space so we can start talking in that language. The idea is to finally, one of the ideas is that to see that this definition of continuity can really be phrased in terms of small balls, which will then we can use as some kind of justification to work towards the notion of open sets and closed sets and some basic topological language. All right, so this is where we are headed. Okay, so the notion of distance, so define.
Sir, I have one question.
Yes, go ahead, please.
So why take a subset S of V and then define F from S to W? Why not just V to W?
Because I do want to have the notion of continuity of a function that is defined on a subset of a space.
Okay, so can this not happen? So like this X is in a like V plus delta to V minus delta region. So can this not happen that X goes out of S somehow?
Right. So, okay. Sorry. Whenever X, you're absolutely right. So how does this definition has to be modified? So whenever X minus V is less than delta, F of X minus F of V is less than epsilon. This is implying that F of X is something that has to be defined, right? But still, in order to make this absolutely clear, what should I say? Whenever X minus V is less than delta, for X in S. Right? Otherwise the sentence itself is meaningless. You see, I'm evaluating F at X. So it makes no sense for X to be outside S. Okay, so I hope that is clear.
Yes.
Yeah. Okay.
Hello, sir.
Yes.
Sir, if we do not get any such X in such a delta region of V, then we consider it to be vacuously true, right? The statement.
Right. So, for example, let us say, take an extreme case. Let us suppose the set S consists of a singleton.
Okay, sir.
Right.
Yes, sir.
Then any function defined on a singleton set it's continuous.
Yes, sir. Yes.
By the way, it is not true that you will never get any such X. You will always get one such X. Namely V itself. I mean, it's a dumb comment, but.
Yes, sir.
Right. But the later part of your statement is true because it's still vacuously true, right? Because when X is V, then F of X minus F of V is also 0. Anyway. Yeah, so define distance. And often we will not even define this distance. We will just say, what is the distance for X, Y, and B? What is the distance between X and Y? It's just the norm of the vector X minus Y. So, you're saying that this is so simple. Why do you even make a definition? The point is that some properties of this distance, we will abstract out and make the definition of a metric space. It's just a useful language to have. Some properties of D. Properties of this function D. Okay, so let's really just go up here and look at 1, 2, and 3. What were those properties? So what does the first property tell you about the distance? It says that the distance between X and Y will be 0 precisely when?
At the same coordinate. There is no-
They're the same vector, right? So that is what that the first one says. The second one, let's put it on the side. What does the third one say?
So triangle inequality x distance from x.
Yeah, so we have to do a little bit of work, but okay, so let us say if I take x to be
Y minus x and z
yeah,
minus
so
y.
you see, right, exactly. So you know, in the third one, I can really change that plus sign to minus, correct? The norm of x minus y is also less than or equal to the norm of x plus norm of y, because norm of minus y is the same as norm of y. Right? So if I look at the left hand side and call it x minus y, then x can be u minus v, and y can be v minus w. Let me do this. So properties dxy equal to 0 if and only if x is equal to y. The second is d of uv plus d of vw. Okay, maybe I should have okay, so I think we can. So what can you say about this?
greater than equals.
And you just see what this is saying. This is saying that u minus v, and this is v minus w. This is greater than or equal to
U minus W.
this is just triangle inequality. Do you see this? Because and then the third one, and you see this, by the way, so this you can see that if I take v to be 0, then this really is equivalent to triangle inequality. There is nothing. So both of these properties, they really are. So maybe I should call this. So this number 2 is really corresponding to number 3 earlier. But also it, let's not write number 3. So let me not number this. Okay, so really I should have just used a different numbering. So this is, so what this says is that the distance, if I scale a vector, if I scale 2 points, then this says that distance between lambda x and lambda y is going to be lambda times the distance between x and y. But of course, what do I have to do? For any scalar lambda. How does this have to change? Come on.
The absolute values.
Absolute value, right? So what we are going to do, so this the third one that I have written, which is really the analog of the two above, is really an analog, is really homogeneous. So what we are going to say is that definition of a metric space. Metric space, let's say X. A set X with a function, distance function. So it is going to be from X cross X to real numbers greater than or equal to 0, such that I have the analog of properties one out of the first two listed properties over there. So let's write this down. Metric space X, a set is called a metric space X if there is a set along with a distance function from X cross X to r greater than or equal to 0 is called such that both of these conditions are satisfied. So one, d of xy is 0 if and only if x equal to y. So you can, by means of the distance function, you can detect if 2 points are equal or not. 2 we will come to. It is not going to be this homogeneity condition. And the 3 is the triangle inequality. So distance of, okay, let's use x, z is less than or equal to distance of x from x to y plus the distance from y to z. So a triangle inequality. But there is one more property. You certainly want the distance from x to y to be equal to the distance from y to x. So a symmetry condition. Is the symmetry condition satisfied here? For our earlier distance formula?
Yes, sir.
Yes.
Because the norm of minus v is the same as norm of v, right? By scaling by -1. Okay. So notice one thing, that this homogeneity condition is not there. In fact, does the homogeneity condition make sense for an arbitrary metric space as defined?
So you don't have any field to pick scalars from.
Right. In fact, there is no notion of even addition. Right. So this is just a set on which you have defined the distance function. Okay. So note.
Sir, if a metric space is also a vector space, then does it imply that the homogeneity will be there?
Okay. Okay. So good. So I suggest that you think about this question for a while. There are some obvious requirements. In particular, do you see that condition number 2 that is listed up there, that has to be satisfied, right, by the distance, if you have a vector space structure, right? Otherwise that metric cannot come from a norm, right? So it's a necessary condition. There is another necessary condition, which is translation invariance. That the distance between x and y and the distance between x plus v and y plus v has to be the same. Just check. If the distance comes from a norm, then such a condition has to be valid, has to be true. But, in general, we want to stay mostly example based. That is, we are saying metric space, we are saying non-linear space, but mostly we are just interested in Rn with the standard Euclidean metric. Right? But the words are going to be useful for us because it is going to give us a language in terms of which things become easy. For example, one of the first payoffs, and by no means it's the complete answer, but still one good answer is that you will see that the definition of continuity will become much easier in terms of this language. It will become it will become linguistically easier, and so it will also become conceptually easier. All right, so note metric space need not be a vector space, much less a non-linear space. There doesn't need to be a zero. There doesn't need to be any notion of addition or scalar multiplication. Okay. And you can say, oh, well, but in practice, what do we have? And you see, in practice also, we have a lot. A very obvious comment. If I take a metric space, and if I just take any subset of it, just any subset whatsoever, just see if conditions 1, 2, and 3 are satisfied. I use the exact same notion of distance. And you see, those 3 conditions are still going to be satisfied. So your non-linear space had to be a vector space, but now I can start talking about, I have something, I have some notion with which to, in terms of which to discuss arbitrary subsets of R, because I still have distance. So any subset under the same distance function. So what we are going to be doing is we will do topology in non-linear basis. But we will often use the language of a metric space. Okay, so let's say using of metric spaces. And we have very little time, but we will get started. And
Sir,
yes.
So the previous point was that any subset of a metric space is a metric space, but any subset of a vector space is not a vector space, right?
Yes, you can just see,
Okay.
no? Absolutely.
Yeah, okay.
I mean, you need not have zero in there.
Yeah. Okay.
Just take any arbitrary subset. So okay, so here's the thing. Our primary interest is going to be non-linear spaces. In fact, even our primary interest is extremely concrete. For the most time, what we want to do is multivariable calculus. That's all, right? So we want to be dealing in Rn and sometimes Cn for the most part. Please do not lose sight of this very concrete fact. That's what we are doing. And mostly we are going to be using Euclidean distance. But we introduce this language of non-linear space and then metric space. And soon we will introduce the language of topological space in order to have meaningful words in terms of which to talk about this. But please do not lose track that we are mostly going to be talking only about Rn. And when we say distance, we will often mean our usual distance. Okay, so without further ado, let us see what open sets and closed sets are.
On a set X, can there be a number of ways of defining metric, or at least a vector space, finite dimensional vector space? What can all be the metrics defined? Like for non, it is always all of them are equivalent. So some characterization of as such is there.
Yeah, but again, you have to say such that, right? With what properties you want. Because again, I mean, so this is a similar question to your question yesterday, and I can give a similarly ridiculous answer, which is that it's an infinite set. So just put whatever, just put it in bijection with some infinite set and put whatever metric you like. For example, there is the following metric. You can see it's the distance between any 2 points is either 0 and 1 or 1, depending on whether the points are same or different. Okay. So distance of any point from itself is 0. Distance of between any 2 distinct points is 1. You should check that the conditions are satisfied. Okay. So of course, if I put such a metric on R, then the topology that this will induce, as we will see very shortly, is going to be completely different. Okay. So, all these questions are very interesting questions. But again, I want to bring you back. For us, we only want to study Rn. We want to do calculus on Rn. So let's first recall. So definition of topology. So ball, open ball in a metric space. With center X in a metric space X with center X in X and radius R. Which is exactly, and I think I made some ad hoc notation, which I will now stick with that notation. I think my radius was the subscript, right?
BRX.
Yeah, right. So B sub Rx is simply the set of all, or maybe, okay, sorry. Let's call the center C just for now. Okay. Center C, radius R. It is the set of all x in X such that the distance between C and X is strictly less than R. Okay. And for the three different norms that we had, we drew pictures of these last time. Okay. So that is an open ball. Closed ball is BRCR, is the exact same thing, but less than or equal to R. Okay. Concentrate on the open balls for now. Those are going to be important for us because now with a drum roll, we have this definition. An open set in a metric space is one of the form which is just an arbitrary union of balls. And a closed set in a metric space X is one of the form, which is a complement of X minus some open set. Okay, so I just threw a bunch of words at you, and we will spend a long time making friends with these things, seeing lots of examples. The very first thing that you should think about, which I will end with, is that you should try to see if you can formulate the notion of continuity in terms of open balls. Okay, so this is a kind of very important exercise in reformulation that we need to do. So you should think of that, and we will take it up from here the next time.
So